Hello and good morning, afternoon, evening, wherever you are around the world. Welcome to the stream. Today we're going to be looking at doing some things in the Nature of Code series. If you haven't tuned in before or you don't know what this is a series where we follow through a textbook on simulating natural systems using JavaScript. And we're doing that with a very wonderful programming library, graphics library that's called P5. I believe I've added some links. Oh, I I need to add the links to the textbook and I guess like the editor that we're going to be using for the stream. But before I do that, or I guess while I have you all here, let's go ahead and get you all checked in to our stream, I guess like workshop link. This is how you get credit for showing up to the stream and make sure that you get credits towards the swag that you're earning this weekend. If you don't know what I'm talking about, we're GHW allows you to earn swag by tuning into workshops just like this one. Okay, so give me a quick moment and I will be adding in the workshop link to the announcement for the workshop today. While I do that, I had some, let's see. It's been kind of cold where I live. This week we just hit above freezing for the first time in a few months. And I just as a quick aside, I kind of forgot that like heaters were a thing. So for a long time I was just like used to having my apartment just be cold because at my parents' house we don't use centralized heating. We just use a fireplace, and I don't have a fireplace in my current apartment, so I can't really start fires. Well, I can, but I don't think there's a safe way to do that besides the stovetop. So I found out that I could indeed turn on the heat, and when I turned on the heater in my apartment, it broke and shorted a circuit. But thankfully, I guess like the contractors, maintenance people, maintenance crew were able to respond really quickly and fix that up. So I've been enjoying a nice toasty apartment since then. And I tried turning it off today to see how I would feel about that. Because I think the cold doesn't affect me as much as some of my friends do. And well, I realized how comfortable it is to just be able to wear a t-shirt in the apartment. So I've just turned it back on again. Anyway, total random aside. I see somebody recognizes the browser I'm using. Yes, that is a very good eye. I haven't tried using Vivaldi or the Qt browser. I was using Firefox for a while and then Brave for a little bit, and Chrome for all of my, I guess, like school related things. But I finally swapped over to Zen because I really liked the vertical bar aspects, and you can kind of simulate that with Firefox. But then, well, I guess something to know is that the Zen browser is built on the Firefox engine, if you're not familiar with it. And you can take advantage of these really cool workspaces, and not just workspaces, but see, I can't really access it here because this is one that's open to a specific workspace, which is my personal workspace right now, which is where I run all my MLH things. But basically, it's like the equivalent of having like Chrome profile or like browser profiles. I think it's really nice to be able to do that. Living life on the edge, yes, yes. That's how you get the adrenaline rush running, right? um, yeah. Well, thankfully, I did buy like a bunch of clothing in case like the heater breaks again, and so I'm like ready for it. Even if the power goes out, I'll have some way of keeping warm. I am thinking of car camping this weekend, um, and putting all of that equipment to the test because I have a nice like sleeping bag too that I'd like to try out, and I just haven't been outside like properly on an adventure in a little bit, so I'm gonna be doing that. I hope. Anyway, I hope you all have an opportunity to go out and do an adventure sometime in the next week or so, just for the sake of doing things differently. Howdy from Houston. I am based over in Wisconsin. I actually have a friend who recently just went, who is also a student here in Wisconsin, who just went to Houston over the weekend. So it's really funny to see another Houstoner out here. I got one of my favorite jackets in Houston actually when I was staffing an event over there. Hack Rice. I got a space themed jacket, which I thought was very appropriate. If you don't know, Rockets are based out of Houston. At least they were for a while for the American space program. Anyway, so let's get to looking at what it is we're going to be doing today. Actually, really funny thing that started talking about Houston. One of the topics in the forces chapter is actually on attraction and gravity. So I'm hoping we can get to that today. We will see how far we can get. So yeah, I guess as a quick overview of where we are, this is the Nature of Code book right over here. And the idea is we're going to be building, I guess, like varying degrees of simulation and just kind of like layering on more and more things to it. Eventually, we will get to, I guess, like simulating creatures and such, creatures that can grow and evolve. But right now, we're working on the physics simulation side. We haven't gotten that far in this series. It's taken about 2 streams on average to get through a chapter, but forces is going to be one that takes a little bit longer. I'm not sure if it's just me, but my stream just cut out a little bit on my screen share. But yeah, this is going to be our 3rd time in the forces chapter. Now, if you think that there are people that can do this content better, that is true. The author of this book actually has his own YouTube channel. It's called The Coding Train. It's a very good YouTube channel. I highly recommend you check it out. He's got all these wonderful videos that will explain it better than I can. But today we're also going to be building things on stream. So if you want to see what it looks like to go through this textbook without having the author's, I guess, like mindset, feel free to continue being tuned in. I'm happy that you are here. Okay, so this chapter we learned about force. We've basically just recently started figuring out how to apply wind force to objects and objects of different masses. And we've been using, I guess, like vectors as a way to do the math for this, because vectors have both magnitude and direction, which is such a fun thing. Sometimes my brain thinks more in memes than it does than it really should. But the way that vectors within this library are handled is they have like X and Y components, and then they have a bunch of math functions that allow us to do handy matrix multiplication and such. I'm realizing I have a comment right here. Was it Maria Dunning? She's helping us host our hackathon. No, actually. But I'm really happy that she's helping host our hackathon. It is always nice to hear about how other MLHers are doing. No, the friend that's from Wisconsin visiting Houston for the weekend is he's like unrelated to Major League Hacking as a whole. But we always do love a good shout out to our lovely HCMs. If you don't know what an HCM is, HCMs are hackathon community managers. They basically help hackathons with logistics throughout the year. And then coaches like myself are the people who show up to events. But sometimes HCMs will also be at events, which is super awesome. You never know exactly who you're going to be getting unless you request people specifically, in which case you get a higher chance of people of being there. Was it Hack Rice too? Oh, that's awesome to hear. Man, I kind of miss Hack Rice. That was my second, I guess, like MLH event ever. And it was a really funny event for me because I kind of ripped my pants at that event. And so I had to politely ask work if I could expense some new pants while I was there. I appreciate the comments. And I also appreciate the refocusing. Feel free to keep on like tossing things in the chat. I think it's always fun to take a nice break from thinking about friction and physics. I myself did not take physics. Well, actually, that's a lie. I took physics in high school, and I took physics in my undergrad. Um, and I got really lucky when I took physics because I took it at the time when COVID was just happening and everybody was trying to figure out how to do remote work. And then 3 out of my 5 homework assignments got drops, and it happened to be that I did really well in the first 2 homework assignments, well enough to get an A+ in the class. um, that by no means is a representation of how good I am at physics, but that's okay. Because this textbook handles physics in a very nice manner. I guess before we get too far into continuing this, I also need to do a quick highlight, I guess, like overview of how, I guess, like the Canvas system works for programming with this library. So very generally, if you remember, I guess, like early math classes, you might be familiar with this normal, I guess, like coordinate system where we have x going from left to right and y going up or down from bottom to up. This is just a quick, I guess, like PSA, public service announcement, saying that for computers, it usually goes in the other direction, at least flipping the y, and then the x continues in the same direction. And the reason why is because, well, I guess like when computers, I guess like render or create contents, we generally know where the top is, and then we scroll down as opposed to scrolling up. And because we know that the top, I guess like we know that our content starts at the top and then goes down, it just makes more sense for us to put our y direction as down being bigger y values. That's something that confused me for a while, and so I want to make sure that every time we do any of these, I guess, like graphics programming things, we cover that. Graphics. Oh, okay. Keep in mind that computer graphics and I guess like the graphics libraries, not necessarily the same things that we're interacting with. But yeah. Anyway, so if we were to talk about where the first lorem ipsum is in this list, the first one would actually be sitting right at the top, right over here. And then if we were to go to the second one, then it would be like this, as opposed to counting from the bottom going up. And so we just want to make sure that our y direction is in a very similar situation. One other call out while I'm here, there's a bunch of other scribbles here. You don't have to pay too much attention to that. But yeah, every, I guess, like object that is drawn within the library that we're using kind of has a different origin point within the object. And this is a thing that you'll have to consider when you're doing things in 2-dimensional and 3-dimensional things and anything that, I guess, like is moving objects around. So the point of origin for like a circle is right in the middle, and then the point of origin for like a rectangle might be like the top left point, as it is within P5. So I think we're going to be mostly working with circles for this chapter because circles are a nice, well, it's a nice shape to just start with. We don't have to worry about orientation since every direction is pretty much the same on a circle. Okay, so let's get into it. Well, not too far into it. I'm going to quickly highlight, I guess, like, hang on. I need to turn do not disturb on my phone because that would be really unfortunate if I got distracted by my phone again. Okay, so earlier parts of the chapter, we talked a little bit about how we started adding in wind forces and mass to objects. Right now, the mass is defined by what's it called? The diameter of our circle. And so, of course, the bigger object right over here has the bigger mass, is the way that we're going with it. In real life, that's not always the case. We're going to go over, I guess, like the structure of this code. It's actually, I like to start over in the sketch.js file, and I'll explain that in just a second. Actually, let's actually start by explaining what this editor site is. This is just this editor page. So technically speaking, you can program all of the P5 things, all of the things we're doing in this stream today. You could do this in your own editor of choice, like Visual Studio Code. Because basically, like this is once again, it's a JavaScript library, so everything lives inside an HTML file and some JavaScript files. So if we actually look at the index.html file, we can see there's not a terrible amount of complexity here. We've got the head tag, and inside the head tag, we just have a couple of scripts and a link to our style sheet. And the style sheet basically just is like a CSS reset, so that when we create our canvas element, it'll just sit nicely against, I guess, like flush against the side of the screen. And yeah, and then we have a couple of scripts down here, which actually connects to the JavaScript files that I was looking at earlier. Those JavaScript files have all of the logic for the actual simulation. Now, the P5 editor right here basically just houses all of the web information right here. And basically, sketch.js has some, I guess, like within this library, it basically looks for wherever the body tag is, creates a element that's called like content or something like that, and then it creates a canvas element from that, in which it then starts drawing shapes and such, just like a real life like art canvas, painting canvas. So yeah, and okay, now I'm going to move over to sketch.js because generally the sketch function has less going on. So let's go ahead and hide these. That way we can just get an overview of what's going on. We've got mover A and mover B just being defined or declared at the very beginning of our file. So we got mover A and mover B. I don't remember which one is which. We've got two functions. So the setup function is a function that runs once at the very beginning, and then the draw function is a function that runs every frame, basically, of the animation. I am seeing a comment asking for a link to the challenge. Okay, so I'm assuming by challenge you're talking about the sign-in link for this workshop. I have a handy-dandy QR code posted right above me if you want to do that on your phone. But if you're already on your phone and you're watching this stream, that make things a little awkward, I will share it in chat. But if you lose it, generally speaking, whoever is streaming at the moment will also link the, I guess, like, the check-in sheet to the Discord announcement. Or if you lose that, you can also always find us over at the GHW MLH schedule. Pop over here, look for the workshop that you're currently in, and we are in the Nature of Code workshop. I guess just as a quick heads up, if you did find this stream from this page, you should know that this description right here is not the correct description, but the workshop description over here is. We are not, in fact, making dynamic web applications by layering JavaScript in. We're basically creating a simulation using JavaScript, though. So similar vibe, different meaning. Okay. So popping back over to this over here, we've got the setup. The setup runs once, draw runs repeatedly. So all we do here is we create our canvas. So that's this white square, if you can kind of see that. It's a little discolored. And then we draw all this stuff. I'm going to actually change this background to be a slightly different color. That way it's more obvious. Colors in this library, just like in many other, I guess, like graphics things, even CSS, is just using RGB values. And so if we wanted a nice blue value, let's see, it starts with red. Maybe we'll do 50 in the red, and then G is green, maybe 50 green, and we'll do maybe like 200 blue. And then if we run that again, it'll be a nice purple. That's a very strong purple, actually. I'm going to tone that down. But yeah, hopefully... Oh, that actually made things not as... Maybe we'll turn this up to 100 each. Okay, whatever. Yeah, we've got a cool little purple, but this should be, I guess, like, hopefully highlights that the canvas element is not indeed the entire size of the page, HTML page, and then the rest of this is just normal website things. Okay. So yeah, create P is just a create paragraph elements. Over here, we created a new mover, and mover seems kind of arbitrary because it kind of is. We've basically just made this abstract idea of something that moves, and this is a custom class that we've made in previous streams. It takes in a couple arguments, 200 and 30. I believe these first two values is just the x and the y coordinate, and then the last value is the diameter. And so mover B is going to be the smaller one. Let's see if we run this again. Oh, right. Okay. Let's see if we want to, we can make it even smaller. So now it's even smaller. And if we want to make this one even bigger, we can make this even bigger. That is too big. But yeah, that's pretty much where the movers are defined. So I'm going to hide that just so we don't get a little overloaded. We draw the background first, and then we apply, or I guess we create a gravity vector. And I'll explain what that means in just a second. But then we apply a force to both of our objects over here. And then whenever the mouse is pressed, then we're going to apply a fan. So if I use the mouse over here, you'll see that the ball just kind of runs away from wherever my mouse is, applies some sort of a force, and then we update where it is being drawn, and then we also check to see if it is hitting an edge of the screen or not. And so inside this function, we are applying a force, I guess, depending on how far away the ball is to the mouse in the opposite direction. Okay, and then we've also got the apply force situation. So the vectors, when we create them, they end up just being a XY coordinates. I think I mentioned this a little bit earlier before. And although I guess like normally when we define vectors, we're used to having a magnitude and a direction, right? This is not in fact a magnitude and a direction. It is only a direction, but this is a direction, I guess like from wherever the point of origin is. And so for these movers, they have a relative point of origin based off of wherever it is that they were drawn. And so in this case, we've got the x value right here and the y value right here. So for gravity, since it's just a downward force, is always going to be pushing down a little bit. In this case, we've simplified it to be just 0.1 of an arbitrary unit. I believe we're just going to assume that this is like pixels or something like that. And then we apply force. Okay, and then the mover is actually going to be defined over here. So let's go ahead and take a tour right over here. So we've got a lot going on in here. Okay, so the constructor, it does indeed take in x, y, and we call it mass, but it's also the diameter. And then we also have a radius function over here for some reason. Well, I guess just in case we want to use radius instead of the diameter. Okay, so then we have an apply force function over here. We can see here that all we do is we just do a vector division on the force and the mass. And then we add in whatever this is to whatever the acceleration is. The update function, I guess something that's also not super intuitive is the way that objects are drawn on computers. I guess in real life, there's always, I guess, like there always exists a state if you can slice time small enough where something just exists between. Like, let's say we're taking my hand right here, and I'm moving it to the other side of the screen, right? My hand always kind of exists between every state, between those two locations. But in a computer, that kind of isn't true. We're always giving the illusion of movements. And so basically every frame is just instantaneously moving from one part of the screen to the next part. And we can do that with just a little bit of math. Velocity, in fact, is basically just adding in, taking the position, the current position, and then we're adding in the amount of distance that it's moved. And that is basically just what our velocity is. And so in the same way, we're to change, I guess, like to apply acceleration, we're just taking a look at how much the velocity is changing, and then we're adding that to the amounts that we're going to be taking a step as far as our velocity goes. And then, yeah, that's pretty much what's going on up here. Our velocity is being changed by our acceleration, and then our position is being changed by our velocity. This is kind of a very classic definition of velocity, distance, and acceleration. We have this thing where we actually set the, I guess, we reset our acceleration at the end of each update. And the reason why is because otherwise, like, we're going to be constantly applying our acceleration. So if I actually hide this, right now the only acceleration that's acting on them, I guess, like, to start with, is just the acceleration due to gravity, which is them just going bouncing up and down. So if I actually run this without resetting the acceleration, we'll see that they bounce a lot faster. And the reason why is because this means that our acceleration is always being added to our velocity, and then the acceleration adds to itself, which is problematic. In fact, acceleration only is applied when, I guess, like, a force is being, I guess, applied to an object. And so in order to reset it while the force is not being applied to the object, we need to multiply it by 0 right there. And so we get a much more normal acceleration amount after we do that. All right, next up, we have the show function. The show function is nice and simple. I like simple things. All we're doing right here is we're saying, I want, I guess, like, an outline for the circle. And the outline's color is going to be 0. It is going to be a hefty 2 pixels wide, so not that heavy. We're just going to color it in. I don't remember what 127 is. I would assume that the fill would actually need 3 colors, and so if we're only giving it 2 values out of our G and B, it's going to just assume that it's like 0, or maybe it was 255. Yeah, I guess it just assumes that whatever value you don't put in is 255. But yeah, and then we just draw a circle wherever the position.x, position.y is, and whatever the diameter is. So we're just taking in the member values from our constructor over here. Okay, and then we have a check edges function over here. So this is basically just seeing if you're towards the edge of the screen or not. Nothing too crazy there. And then we've got the fan function. So this fan is the thing that makes it so that the balls get pushed away from wherever the mouse is. So we do that by seeing how far away the mouse is from wherever the position is, and then we check to see if it's to the left of the fan or to the right of the fan, and then we apply a force in whatever the opposite direction is, or I guess more so in that direction. Okay, so that should pretty much catch everybody on the stream up with where we are at this point in time. Okay, so now we can actually get to looking at friction. As you noticed while I've been yapping, these balls have been bouncing on forever and ever. And like when I apply a force, they'll just continue, I guess, like bouncing on and on forever as well. They don't really slow down, which is bad if we're trying to make some sort of a simulation that eventually, I guess, like, is closer to real life than completely artificially simulated. Give me a moment. I made some tea and I need to take a little sippy. Sorry, as a quick aside, I've got this, I guess, like, newish tea mug, and it's like a tea mug and a bottle at the same time, which is pretty cool. Eventually, I will probably try investing in a kettle that is a bit more like tea size because, or like allows me to tweak the temperature that it comes out at. Because I had to wait 30 minutes for this thing to cool down enough for me to not burn my tongue on it. Anyway, tea bottles are pretty cool. This one, you can see it. It's got like a tea bag sieve at the top. Let me actually turn off my virtual. How do I turn off my virtual thing within this? Da 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 da. Okay. So it's got this the tea bag kind of thing, reusable kind of thing, and I can kind of open it and put it in and out and in and out. I'm not sure why I would bring it up. Maybe if I'm not drinking tea, I don't know. But this is my first time using it, so it's been pretty cool. I see somebody's asking about what the tea bottle brand is. The tea bottle brand is Aladdin. I'll type that in chat. Oh, and I missed the E. Okay, but I think you got the point. And the kind of tea I am drinking is, I believe it's black tea. It's some sort of Chinese tea. Unfortunately, I'm not literate in many ways, and I can't read Chinese, so I don't know what kind of tea it is. I believe it is black tea, though. It's slightly caffeinated because right before this stream, I was really exhausted and needed to sleep, but my heart can't handle energy drinks, and I probably don't need that much caffeine to stay alive. I'm trying to not be too much into that. Okay, anyway. Not sponsored, not a product placement. I just enjoy tea. Looks like we've got some people enjoying tea in the crowd too. Oh, you're drinking tea as well? Okay, what kind of tea are you drinking? Do let me know. Okay, is black tea as well? Okay, we'd love to see it. Okay, so I'm not going to read this word for word. I am going to try to highlight, I guess, like whatever I think is important as we go through it. So friction is something that causes us to lose energy. Okay. And I know this book talks about it later, but right now, I guess like if you've taken a physics class, you may remember that there are, I guess, like elastic and perfectly elastic collisions and inelastic collisions. Right now, we're simulating an inelastic collision, and where no energy is lost at all. But of course, real life doesn't work like that, so we need to find a way to simulate losing energy. We've got some more tea representation, kind of just hot water over here. I do recommend adding in some leaves. It adds a little bit of flavor. But I do respect the hot water. It helps warm the soul. We got a raspberry leaf and hibiscus. That sounds really lovely, actually. Really flowery. Speaking of flowery things, sorry, another aside. If you've never tried flowery ice cream, it's a very interesting experience. Like, I don't know how else to describe it other than flowery and an interesting experience. And I don't mean interesting in like a bad way. I mean, like, you just don't have the vocabulary for it, unless you've tried it yourself. Or I guess that didn't add any more vocabulary to me. Like rose, which flower? That's a good question. I am going to look up flowery ice cream. Usually it's like ice cream shops that will have it, and because usually the ice cream that you would get at like a grocery store won't be adventurous with the kinds of ice cream that they make. But yeah, I guess yeah, you can have rose ice cream. I do remember having a lavender and a jasmine ice cream. It's kind of like tea like almost. But I wouldn't say that it tastes like tea because there's also like tea ice cream as well, I will say. But yeah, they usually mix it with something else. I think the one that I've had that was with lavender had like pecans in it or something like that. Lavender's bomb. Yeah. Yeah, I do recommend if you haven't had it before, it is worth a try. To pop over to your local ice cream shop and try that out. Okay. Um, it's really funny seeing you say lavender's bomb because I think about lavender like bath bombs. I feel like that's the only kind of flavor of bath bomb I can think of. All right. Let's see. Kinetic energy converted to thermal energy. We're not simulating thermal dynamics though, because that's a lot of math, and that's pretty. We're not going to see, I guess, like a lot of change. If we don't include the thermal part of the simulation, unless I guess we're working with like ice and stuff. But like, we're just going for a simple fluid simulation for today. So yeah, we're going to be focusing on just kinetic friction to make it so that it eventually stops. Now I did scroll ahead before the stream and just make sure I copied over, I guess, like the example that this part is building towards. And so basically, actually, let's reset this. We've got our bouncing ball, and you'll notice that it is kind of slowing down a lot. Also, it's a little wide. Let's actually adjust the wideness of this thing so we can play around with it a little bit. We're going to make this a square canvas. Oh, that's really small, actually. We're going to make this a rectangular canvas, but maybe less wide. So if we go over there, yeah. Let's actually just make it an even 400. Yay, okay. So yeah, it eventually does slow down, whereas if we were to poke back over here, this thing's going to go on until the end of time. Heat, death of the universe and stuff. So yeah, I think the textbook is basically just going to do some physics lore drops while we are going through this code. So I think it would actually, I'm going to get a little distracted if we keep on bouncing between the textbook and the code. So what I want to do is I kind of just want to go through this code that this example is going through. And then we're going to look at the textbook and see if we missed any context here. Because I think we've got a decent bit of code literacy on our side. So we should be able to read what's going on over here. So I'm going to go ahead and hide these. Before I do that, I see we've got some comments. Need to try. You're influencing on this stream. Yeah, I appreciate the banter in the comments, y'all. Okay, so let's take a look at the setup. So nothing crazy. We've got a mover that is starting in the middle of the screen at about 30 pixels high, or I guess from the top. So it bounces however much 240 is minus, I guess, like whatever the edge of this circle is. And then we give it a mass of 5. Okay, cool. And then we give a little function to just say, yeah, you can use the mouse to apply wind force. Okay, we've got a background. I'm going to go for a different color background because I like to have different colored backgrounds. We're going to go for maybe a greener one just because I don't want to move that first value. And well, this should bring us to something that's nice, very nice. My color theory is really bad. I, for some reason, thought that was going to be more green. I guess it's more, wait, oh no, it's red. Red is the first value. Blue is the last value. That makes sense. Okay, yeah, so we got a pink background. We're going to roll with that. Okay, so then the next thing is we've got gravity, which is kind of heavy here, actually. It's a whole value of 1. Previously, we had it at 0.1. 0.1, not 0.01. Okay. And then we've got a note here. I should scale by mass to be more accurate, but this example only has 1 circle. Okay. So the reason why he's saying that is because of the world famous F equals ma function, I'm assuming. But like in our simulation, we have mass attached to diameter anyway, so Not too big of a deal here. Cool. All right, and then if the mouse is pressed, then we apply winds. Okay, that's not too crazy. Ba, 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 ba. If the mover hits the contact edge, so contact edge is something that's new to this simulation. Previously, we had like edge detection, but I believe contact edge is the thing that we're going to be applying, I guess, like the friction to, which is, I guess, like the little itty bitty part of the circle that is actually physically in contact with the sides of the walls. So that's the bit that we're going to be losing friction over. Now, if I remember anything about friction, there's something that's called the friction coefficient of materials. And so the friction coefficient basically tells us how much an object slows down another object when it is, I guess, like on it. And there's two types of friction. We've got what's it called? Static friction and sliding friction. Okay, and so static friction is when something, I guess, like that's how much it resists movement, and then we've got sliding friction, which is how much it slows down while it's moving on it. And so I would say in our simulation, we're more concerned about sliding friction than static friction, since we're talking about slowing objects down and not having enough force to actually overcome the static friction in order to move something. Vietnam flashbacks to university physics. Yeah. Trust me, it's been getting me too. Even though I got really lucky and I got my A+ in physics because a lot of my homework assignments got drops. It is nonetheless not any less terrifying. Okay, so okay, so we haven't seen this before in the stream. The copy function, which I'm assuming does exactly what it sounds like it does, and copies over the friction, the current velocity into the current friction. And then we're multiplying it by -1, which is to make sure that it opposes so that it slows down instead of accelerating, I guess. And then we set the magnitude for this to be c. So the reason why we're copying the velocity instead of, I guess, like computing it ourselves in any meaningful way is like it's really easy for us to grab that. Let me actually pull this over here. Now I'm sorry if you are like really good at physics, or maybe not even that good at physics, but able to follow what's going on here. That I'm going to be taking things a little bit slowly. Why is friction backwards? I'm just going to be doing this because I need it. Okay, so if we've got a force where this thing is pointing in this direction, this is our, I guess, like our current force. Wow, it's so big. Okay, cool. And then so we've got the friction force. This, I don't remember the shortcut for this. Okay. So we're going to attach that. Current force, and then we've got the friction force. Okay, so then this is just going to be really small, and it's, okay, so we've copied it, and then we've made it negative, and then we apply the C as 0.1, so we just made it smaller. I'm just going to put this as F, just so that we know that it's different. I'll call this force. Okay, so that's basically all that is that we're doing on here. Set the magnitude, and then we actually apply the force, so that's not too crazy. All right, cool. And then we've got the bounce edges, update and show. I don't believe there's anything crazy going on here. This should be pretty similar to what we had before. So let's go ahead and hide all of these functions and look at them one at a time. Apply force. Yeah, that looks pretty similar to what we had before. That's the same. We're also just drawing things the same. Contact edge. This is the new function that just determines if the mover is touching the edge when it's within 1 pixel. So it takes the current y value. It is greater than the height, where height is a keyword that talks about the canvas height, minus this dot radius, so how far from the center it is, minus 1, which is, I'm assuming, yeah, the 1 pixel bit that we're talking about here. So if we'll notice over here, we actually have another 1 pixel that sits right above wherever that line is. And that pixel is because our circle has a stroke weight of 2. So if we actually made that 1 instead, this entire thing should, the entire black line should sit underneath wherever the border of the canvas is. Or maybe not. Maybe it just, I had my math wrong. Okay, anyway. I've got a question about connecting Discords and DMs later. I personally do not like connecting over Discord DMs. It gets really messy. I would prefer if you, I guess, like put it either in a more public channel so that other people can see it, especially if you've got something cool that you've built. I think it's cool to share in public spaces instead of private spaces. I will just leave it at that. But I'm glad that you've got something that you're excited about sharing. Okay. Okay, cool. So I think we've already covered the really big changes within this file. Let's go ahead and look at the textbook to see if there's anything different or anything extra that's been added. And normal force, which is the force perpendicular to an object. Basically, this is how much force an object has that is resisting motion, I suppose. And then we've got c is equal to 0.01. It was arbitrarily set at that value. Coefficient of friction, the strength of the friction force for a particular surface. Okay, that's pretty similar to what we were saying. Angles in trigonometry, we're not going to worry about that. Gravitational attraction, we're going to worry about that later. We have a normal force. Now that we have magnitude and direction, we can put this together in code. So we've got now the friction coefficients, the normal force, the friction, the magnitude of friction, which is basically just going to be 1 times 0.1. And then we do the copy, we do the reverse, we do the normalize, which I guess is the thing that makes it not as big, because it removes the magnitude, how far it's going. Yeah, this code calculates a friction force but doesn't answer when to apply it, and so he goes on to say that we can apply that whenever we want. So we're doing this whenever it touches the edge of the canvas. And then he talks about the idealized elastic collision. This may be just a me thing, but the idea, or just this phrase of, oh, maybe he doesn't say it here, but the phrase of a perfectly elastic collision is very funny to me, because I guess, okay, so elastic versus inelastic collisions. Okay, so elasticity is how much something, I guess, like moves, right? When, or how much an object deforms when it encounters something else. So a perfectly elastic collision is something that would just completely, like if it hits like a wall, for example, like let's imagine this is like a plate in a paper and it's perfectly elastic, then it would just like kind of crumple and just go. And so for some reason, like I always imagine just like a little like slime ball, or maybe like a normal, like a soccer ball or something, coming up against a wall, and it just goes, and And I just that imagery of a ball that just goes splat is just very entertaining to me. So whenever I think of perfectly elastic collisions, I think about that. And then perfectly inelastic collisions are things that don't deform at all. So it's very much like a heart, like a pool ball, like a billiards ball, just like hitting a wall and going like that. If I got that right. Yeah, but yeah, there's no such thing as a perfectly elastic collision, um, meaning no kinetic energy is lost when they collide. Oh yeah, because momentum and things. I guess like if this wall was not a wall and if it was like another object, then they would technically like kind of both move. I think that's what he's talking about there. Okay, bounce edges. Did we look at bounce edges? Oh, we did not look at bounce edges. I think that is a function that has changed. Let's look at that. Hide everything except for bounce edges. Oh yeah, that is definitely something that changed. So made it so that we lose 10% of the velocity every time we bounce. So then we took this function. This is just checking to see if we pop over to the right side, and then we take the position, we reset it to, I guess, like wherever the right side is, and then we multiply it by the bounce, which makes sure that we lose velocity, or like as magnitude. And then, yeah. So normally we would have to make sure that this goes in the opposite direction, but because there's a negative sign here, that means it's always flipping each time we do the math. So we don't have to do any more negative things over here, which is nice and handy. And then we don't have to worry about the y being bigger than wherever the starting point is because it isn't bouncing off the ceiling here. And there's no reason for it to. Okay. Thanks for the ping. I will take a look at the ping after this stream. I appreciate the excitement. And I look forward to seeing your project. Okay. So let's keep on going. This is the example that I've pulled out over here. And so if we look at this and we reset this, very much does the same thing that we were talking about. Okay, so now we've moved on to the first exercise, exercise 2.6. It's a physics-related project. Okay, so that seems like a very relevant thing. You know what? Usually I don't like to look at these projects on stream. Let me look to see if this project is something that I can bring up on stream. So I'm going to open up on another page first. Oh, I am having trouble accessing this project right now. I'm sorry. I'm going to let you... Oh, maybe it's because there's an exclamation mark at the end. Ah, okay, I found it. Okay, so this is the project that M Paperclip has shared. This is actually a really cool project. I want to... Oh, okay, hang on. Let me refresh the page. That is really satisfying. So if we reset this scene, we have a very heavy gravity. It doesn't even bounce. All right, I want to increase the bounciness. Oh. Okay, so I think that one was a little too heavy and went through the entirety of the world. Yeah, this is you probably know much more about this than I do, and you've already programmed a very awesome simulation that's much better than what we're probably going to be doing. But do you have any fluids yet? Any fluid simulation? That's what we're working on. So hopefully you'll get some inspiration from this workshop to continue working on this, because this is a sick project. Whee! Okay, so yeah, thank you for sharing. I really appreciate it. I'm always a little nervous about opening up people's projects on stream. Um, but I appreciate you for being more reasons why I can trust this community. Okay, so let's look at this exercise. Add a second object. How do you handle having two objects of different masses? What if each object has its own coefficient of friction relative to the bottom surface? Would it make sense to put the friction force into the mover method? So let's move back over here. Actually, no. Let's stay over here, and we will update the example to the exercise after I take another sip of tea. Okay. Well, the first step, I think, is for us to just pop over here. And let's go ahead and add another mover over here. Mover B, mover A. And we're going to go ahead and look for wherever we see mover. And we're just going to go ahead and update that to say mover A. Mover A, 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 A. So many A's. Okay, cool. And let's just double check to make sure that this thing still runs. And let's see if friction is working, doing its thing. It looks like it is. All right, cool. So now let's go ahead and copy all of this to get to mover B. Okay, so we wouldn't actually need to do the friction thing again. We just need to apply the very end results of whatever that math is. And then we will run all of this down here. Okay, so I know there's some of you in the crowd that's probably screaming, or at least has a little conscious in your head screaming about how this is bad programming practice and we're not scaling, we're repeating ourselves and do not repeat yourself principles. To which I say, yeah, my brain is screaming that right now. But that's okay. We don't have to worry about it. Don't let perfect be the enemy of good. We just want to make sure that it works with two people before we can continue scaling it. That's not the expected behavior. That's really interesting. Oh, did we just lose one? We did just lose one. How did that happen? Is it because it's not bound on the left side of the screen? Oh, it just went up. Well, that's very interesting. Everything else is pretty much the exact same, except maybe I want to say it's probably we're not applying gravity to it. Ah, here we go. Okay, but because they started in the same spots, we can't actually see where it is. Let's actually make this one a little bigger. We'll make it twice as big. So the gravity function is still working as expected. It's actually being drawn on top of the smaller one. Cool. It's also more bouncy. It's a big, jolly bouncy. Okay, and that still works on the left and right. I can't actually tell if the friction coefficient, well, that seems really wrong. The fact that this thing is sliding so much more than the other one. So I think that's probably the thing that we're going to be adjusting when we adjust the friction coefficient. Okay, so I think what we're going to need to do is, if we want to adjust this, is we should take this, copy this, remove this over here, remove mover A. we'll put mover B over here. Just replace those with mover B, and then let's increase the coefficient of friction to 0.5, and let's see if that adjusts. Okay, yeah, that seems like it's been moved properly. So then the next question is, does it make sense to encapsulate the friction force into the mover method? I suppose it depends on how you're structuring this project. Like if you want to make it so that the balls themselves have different materials, then it would make sense to adjust that. But I think the more important material for the coefficients is the material at the surface. So I would hazard to say that we should, yeah, indeed, abstract out the coefficient of friction from, I guess, like the specific movers. Because if this coefficient of friction was applied within the mover class over here, that would make things rather annoying because we would have to update our class and abstract away the coefficient of friction. Thankfully, the way that this class is designed is we just do the coefficients outside. Now, I think it would be a lot handier instead of having to do all of this logic outside of the mover, to actually create a new function that can take in the input of a coefficient of friction. So let's go ahead and do that real quick. I don't think that should take too long. We're going to hop over here. We're going to turn this into a probably a what kind of a function is this? Okay, so this would be apply friction. Toss this in here. All right, let's toss in C, or actually, I'll probably spell it out. Coefficient of friction. No, that's too much. Coef friction. Yeah. All right. So then we'll just call this dot contact edge instead of over B, and then everything else should be pretty much the same, except we would put in coef friction wherever we see the word C. Coef friction. And so now we should be able to just do apply friction. Mover A dot apply friction. And then the coefficient of friction for this first one is just going to be 0.1. I know, I'm sorry, magic numbers. Apply friction, 0.5. Let's just see if this works before I give it a proper thing. Okay, that looks like it's working to me. I'm not really going to do the math to make sure that that is doing all the math right. that math is close enough for me. Yeah, let's. I think that looks pretty good. Okay, so then the next thing is, where did my friction things go? Okay, it would probably be good to actually mention what this is here, but I guess I don't know how much longer we're going to be looking at this specific example file before we move on, because I do think we're going to be moving on to fluids pretty soon. Yep, air and fluid resistance. Before we do that, exercise 2.7. Actually, let's save this. GHW forces 2.6. Exercise 2.6. I don't remember what my naming convention is for this. And I will add this to the Discord announcement after the stream if you want to get access to all the stuff that we were playing around with. Okay, so instead of wind, can you add functionality that allows you to toss the circle via mouse interaction? That's a rather interesting exercise that doesn't seem to really be talking about what we've been doing. I think it's going to be more interesting if we move on to the fluid resistance things than it is for us to add a new way of tossing things around. So with y'all's permission, I'm going to scoot on forward. If you want to try to go ahead and do this, please go ahead and do that. I think there's more value if we keep on going. Okay, so I'm going to do the same thing that we did earlier, which is we're going to have the example on the side, and then we're going to look at the code first before we look at the explanation of in the textbook. So first thing I'm going to do is I'm going to scoot all the way down. We've got a lot of math going on. There's some more code. Let's take a look at this simulation. There's something kind of haunting about that. It kind of feels a little bit like, maybe this is just me, but I very recently rewatched the Pirates trilogy, Pirates of the Caribbean trilogy, and I'm reminded of sinking people. That's a little morbid, but just the way that they touch down is just really jarring to me. Okay. Oh. Especially with the way this just says bodies. Okay. All right. Let's try to explore this, and then we will hop over to the textbook to see if we need what extra context I can add. Okay. So demonstration of multiple forces acting on the bodies. Oh, I thought the mouse was continuing to do the wind force. Okay. Bodies experience gravity continuously. They also experience fluid resistance when in water. So maybe what we can do just to demonstrate our, I guess, like knowledge here is to add in wind force to this example. Or maybe that's going to be part of one of the exercises. I don't actually remember. No, the exercises do not in fact touch the wind force. They do something very different. Okay, so let's try to get through understanding what's going on here before we actually do that. Sorry, I recognize a lot of the stream's just been me sipping on water, but the tea was getting cold, so I didn't really want to drink cold tea. Made sure to finish that while it was still kind of warm a little bit, at least a little bit. Okay, so experience fluid resistance when in water. So we need to find ways to, I guess, like additively consider all of the different forces that we're looking at. Instead of listing them out one at a time, we are indeed going to put everything into an array. Very good. That's good programming practice, I think. And then we just make a liquid exist. I imagine we're just simulating, very roughly approximating what liquid is by saying as soon as we're below the certain y threshold, we're just going to say that's where the liquid starts, or the liquid functions start. Okay, so it looks like the liquid is actually a object itself. It's going to start, I don't know what all these parameters are, but we'll find out soon. Usually the height is, okay, here's my guess. This first height is dividing it by 2. So I'm guessing it's actually drawing a polygon. And then this is going to be our friction coefficient, is my guess. So we'll come back to figuring out what those values mean after we look through the rest of these functions. Okay, so then we draw the liquid. Cool. We check to see if the liquid contains the movers for every mover. We look at the drag force. So I'm assuming the drag force is considering the mass or the surface area of the mover that's going in the water. Then we just apply the drag force. Okay. Not too crazy. Gravity is scaled by mass here. Okay, so then we apply our normal gravity here, and then we just show things as normal. All right, not too crazy. Mouse pressed, reset. All right. Reset. So every time we reset, looks like we have 9 movers that we spawn, and the distance is 40 pixels plus wherever it is that we're looking, and then we give it a random size. All right, not too crazy. Let's pop over to mover, since that's another function that we're familiar with, just to make sure that nothing crazy is going on over here. Okay, so we actually have reduced and don't have any more of the, I guess, like wind force functions in here. So I don't imagine there's too much that's crazy. Yeah, apply force is pretty much the same. Update is pretty much the same. Show is also the same. Check edges. Check edges. Yeah, it still has, I guess, like the amount of, this is the inelastic collisions, I guess, and losing energy efficiency every time it bounces off of the floor. So that's our dampening. All right, cool. So yeah, nothing too crazy. This is very similar to what the original mover class looked like when we initially made it. So let's pop over to the liquid.js. Okay. So constructor class, the x and the y. All right, so it starts off at x is 0, and the y is twice the width. I guess this is where x0 is. Or sorry, half of the width, so then half of the height. So then it starts all the way down here. And then the width is the entire screen, so it should be the entirety of the width. And then the height is also half of the thing. Okay, so yeah. And then C is indeed the, I guess, the liquid friction coefficient. All right. Is the mover in the liquid? So we're just checking to see if it's within this general area. We have this pretty big, I guess, like, Boolean check. I would actually have preferred it if we'd taken it out into something like this. Position.x as greater than this.x. So I guess if it is less than, sorry, greater than the water's x, position.x. So that doesn't really make sense. Why do we have this if we're not really moving left or right? I was going to say I would prefer it if we extracted all of these Boolean statements out here. Is right is equal to something like this. And we toss this in so that we actually have, I guess, like all of the statements. Because otherwise this can be a little bit hard to read if, for example, it's moving too far to the right and we know that it shouldn't be. This is just helpful in debugging later. I'm not going to worry about that. We're just going to, we know that this works. Okay, let's actually look at the spicy things, which is the calculate drag. Calculate drag, magnitude is the coefficient times the speed squared. Okay, so I think that's going to be just like the reason why is because it's of a physics formula. That's not something that's done specifically because it's a programming thing. So the speed is equal to the current velocity magnitude. That is fair. Speed does not have direction. It only has strength, size, magnitude. All those things are the same. Okay, and then we're going to multiply this. Oh yeah, this is probably just the physics thing. So the coefficient times speed squared. That makes sense. Direction is the inverse of velocity. Okay, so then predictably we copied the velocity, put it in the opposite direction, and then we set the magnitude to be the drag force, and then we return the drag force. So this is just calculating drag, and then we then pass that drag over to the mover as I guess like how much it slows down, and then the show is just coloring it in. If we want to make this blue, I always enjoy just trying to make it a little more lore accurate as far as the colors go. Blue is the last value. We want this to be kind of a lighter color. So we're going to do maybe 180. A nice turquoise, I think, would be a nice color. So we're going to try to make it so that the green value is a little higher than the red value. Let's try that. That is not as turquoise as I was hoping. There we go. That's a nicer blue, I think. It's very calming. Okay, I'm procrastinating. Let's hop over to the exercises. Actually, before we do that, I want to make sure that I'm understanding that the magnitude is indeed just a math physics thing. Let's look at where the magnitude is. This is the physics function, speed squared times the coefficient of drag. And the direction is the opposite of velocity. Yeah, that makes sense. To me, at least. If it doesn't make sense to you, feel free to toss it in the comments and we'll explore how to make more sense. But for now, we're going to continue on to the exercises. Okay. We'll stretch break. All right, we got 40-ish minutes to do this. I think we can do this. I don't think we're going to get to gravitational attraction by today's stream, but hopefully we will get to that on tomorrow's stream. So hope to see you then. But let's keep on going. You may notice that if you set the coefficient of drag too high in example 2.5, the circles may bounce off of the liquid. This is because of the large time steps. So let's actually pop over to sketch.js and see if we can find this experience. Liquid.show, calculate drag. Where's the coefficients? Oh, right. The coefficient of the liquid is defined up here. So let's make this 100 times stronger. Oh, wow. Some of the balls just straight up deleted. That's actually really funny. So I don't know enough about physics to know if what a high coefficient of friction for a fluid means that it's more like viscous, like if we're looking at honey, as opposed to water, because water you can move around in that relatively easily, but like honey is too thick for you to move around in very heavily. And by honey, I just mean like the honeybee honey, like yeah, like this. Like water doesn't do that, but honey does. Okay, so right now that is too high. I wonder where the limit for how bouncy it is. So it's actually definitely 0.5, 0.3, specifically for the very small objects. I guess that's kind of true to an extent, where like if you have it thick enough, you can probably like dribble a ball off of it. That means it's not very fluid, I guess. Okay, cool. like non-Newtonian fluids, oobleck kind of vibes. If you grew up in the United States, that might be familiar. One of the science projects that we do is we make this. And if you're familiar with the Metal Gear Solid, the Metal Gear Revengeance meme of nanomachines, hang on, nanomachine son meme. They harden on impact. I swear, I'm looking this up for a reason. Here we go. Basically, it's just this game franchise where they have nanomachines, and this guy he has this quote, and it's kind of corny, where he just says he explains why he's not taking damage, and he's with nanomachines. And I'm saying this because this is what like oobleck does. They harden in response to physical trauma. So it's like if you're hitting it really hard, then it like kind of like bounces off, and it becomes a different kind of collision. So that's what like oobleck does. Oobleck also does that. Hitting oobleck. Yeah, you can kind of if you punch it, it hardens on impact. So I think that's what the nanomachines are kind of referencing. Okay, and so I think if we have a high coefficient of friction, I think like oobleck is something that would have a high coefficient of friction. Except it's kind of weird. Oobleck itself, I don't imagine that people would enjoy writing a simulation for that. Okay, love getting distracted on this stream. Whew. Okay, can we use the vector limit method to correct this issue? You might try dropping the objects from variable heights. How does this affect the drag as they hit the liquid? Let's start by looking at the P5.js documentation. Let's look for vectors. Not vector. Let's look for a limit. Limits the velocity to a maximum value. So, okay, that seems rather trivial then. I think inside, it would make most sense to me to go in here and just apply a limit function to apply force maybe, or maybe it's update. Let's add a limit function to acceleration, or this dot velocity dot limit, and then we're going to cap this at like 100. And so nothing crazy should happen yet until we pop over here and we increase our coefficients to, well, I know it started happening at about 0.3, but let's be a little bold. Let's put it at 0.5. I think 100 is probably too high then. Too high of a max value. So let's pop back over here. Where is it? Let's be boring and cap it at 50. 50 is still too high. Is this even doing anything? Let's actually put it at 10. Okay, I don't think we're actually... Let's limit it at 5. Okay, that was a bad run. Most of these were above. So all of these are still bouncing pretty high. I guess 5 is the amount of pixels it moves at any time. Put this at 3. Wow, we have to have a really low limit in order to make sure that it doesn't clip through and bounce really weirdly. I have a feeling we're putting limit in the wrong place for this exercise. You might also try dropping the objects from variable heights. How does this affect the drag as they hit the liquid? I don't think that's a hint towards that first part of the exercise. Use the vector limit. Okay, so I suspect that's not going to solve our problem. Let's actually put it... Actually, okay. Let's put this at the limit of 1. That was really sad. These things are barely moving. Maybe it's an acceleration thing then? List of velocity to add. Can we cap acceleration? I'm going to remove this comments because I don't like how it pushes everything so weirdly. Oh, that's probably happening because, yeah. This entire line was just too long. Okay, I'll keep that here. Okay, let's try capping acceleration dot limit. Let's cap that at 1. Okay, I think that was maybe too high. Cap that at 5. Okay, cool. Oh, I guess we found our acceleration thing. I think if we were doing things a little bit smarter, we probably could have used a little bit of logic to look at liquid instead of just looking exclusively at the other one. Because I believe, let's see, mover velocity, drag force multiplier, and I believe the reason why acceleration was getting too big, yes, because when we were applying the magnitude of on the acceleration thing, then this is the place where acceleration got too high. That makes a little bit more sense to me. Okay, cool. So I think we had that. We may also try dropping the liquids from variable heights. I don't know that would do anything meaningful. So I'm gonna hop over here and we're gonna try doing that. The x is the first value, the y is the next value. So let's actually make this like 100. Oh, right. I want to make this drop from higher. So we're going to start it off there. Okay, cool. That seems like it did a thing. This liquid seems really like heavy, but I guess that, yeah, we did make it very, very thick. All right, cool. The original formula for drag included surface area. Can we create a simulation of boxes falling in the water with a drag force dependent on the length of the side of hitting the water? First off, let's actually go through here and just do forces exercise 2.8. Let's save this. And then I'm going to duplicate this. And then this is just going to be exercise 2.9. Okay, now we have a saved working copy somewhere that we can revisit. Okay, so first thing I believe we're going to need to do is we're going to need to change these into boxes instead of circles. So let's go ahead and do that. So in P5, I believe it's just rect. Yeah, there we go. We've got all of our boxes now. We need to adjust the radius. I guess the point of origin for wherever the check edges is. Although it is kind of funny to the boxes is just I don't know why the boxes are so much funnier than the balls. Okay. Position dot y is equal to that, and the radius. Let's just make this. Do we have a diameter? I don't remember. We don't have a diameter, so we're just going to multiply this by 2, and that should make it so that they actually stay on top. Oh, that's that's really funny. Okay. They're like jumping. Dampening when hitting the bottom. This dot position dot y is equal to this dot radius. I think we need to update our check edges function. Let's pop over. Is it here? No. Check edges. Where's our check edges? Oh, that is the thing that we updated. Okay, let's see what else is being applied. Check edges, show, and update. Here's the old CD player effects. A little bit. I don't actually remember which CD player effect. I know I grew up watching CDs with different effects. I don't. Are you thinking of the one that has like the Okay, now I need to look this up. Old DVD effects or CD. I think it's the screensaver effects, right? Is that what you're talking about? I'm kind of getting something. I'm reminded a little bit of this, but I don't know if I can. Yeah, okay, cool. I don't remember what the. Oh, this is really funny. A 10-hour stream of that. That reminds me, I've been thinking about there's like a bunch of like low effort YouTube channels that just like do those kinds of videos where it's just like a screensaver kind of thing that just runs for like X amount of hours. Like imagine how much bank the person who has like the log or like the campfire fireplace log that just has like a little bit of ambient sound. Imagine how much money that person makes from that like one really low effort video that's just like 10 hours long or something like that and has like really high retention rates because people just set it and leave it. Anyway. The one that displays on the player or the hardware screen. DVD effects. The player. I don't know what the right keyword search is for this. DVD screensaver effects. Is it like a DVD thing, or is it like just a normal like piece, like an old like PC screensaver? I think about the 3D pipes one. Let's see. Oh gosh, these are violently old. Okay. If you find the specific keyword search for it, please feel free to drop that. I'll bring that up. For now, I want to figure out why these boxes keep bouncing at the bottom of the screen. Okay. Let's see if it's down here. Calculate drag, show, rectangle. Nope, it's not going to be that. It's not going to be that. Check edges, resets. It's not going to be the resets. Apply force, apply gravity. Check edges. It's dampening. If I just hide that, does that work? No. Oh, that's why. That's because the if statement is just this check edges thing only works if it was actually below this other section. That's the reason why it was jumping like that. Okay. So included surface area. Can we create a simulation with a drag force dependent on the length of the size side? I mean, like technically speaking, this kind of already does that just with mass instead. So the only thing we would need to change is when we make the box. I guess when we look at the drag force, instead of calculating based off of the mass, where is it? Speed, the velocity magnitude, drag force velocity. Hang on, I need to read. I have a noodling of what I'm thinking about, but it's not formulated enough to articulate that. Gravity scaled by mass. Movers apply drag force. Drag force is equal to calculate drag. But the calculate drag doesn't actually do anything with the mass at all. The only point where mass is being affected is by velocity. And velocity is only being affected because of acceleration. Yeah. So this is the only point where mass would be affected. So if we were to, it's not as simple as, well, I guess, okay. I think mistake number one is that we didn't actually look at what the original formula for drag is. So let's actually scroll back up until we can find the formula section and look for the surface area part. Oh, here we go. Okay. The surface area is A, where C is the coefficient of drag. And we have rho, which is the density of the liquid, which we are not considering. So then I guess what we would be doing is we would just be, okay, where's the magnitude? So I believe all of this over here, this is just handling the force of the drag. Force of the drag. So then it handles the negative 1/2, I believe. Does it handle the 1/2? Written the simplified formula as a lone constant representing the coefficient of drag, but we can think of this as all of the math parts combined. Ah, okay. So then really we would just be adding in, I guess, the surface area right here times surface area. So then it would be this dot. We'll have lowercase sa. Maybe we'll have uppercase sa. SA. And then we'll pop over to mover. We will add in this dot. Oh my gosh, this is getting hard to read just because of, I'm so used to, like, I don't like how it does the line break whenever it's too wide and it like resets back on the next line. Like that part makes it kind of hard for me to read. Anyway, this dot SA is equal to mass divide by 4, I guess. The mass, so for a rectangle, sorry, for a square, the length of each side is the equivalent of like the radius. So then, yeah, it would really just be whatever the mass is again, because our definition here for mass just has it such that the square itself is defined by how wide the side is, and we're using this exact value right here to create our square with the radius right there. This dot radius times 2. Okay, yeah, I mean, oh, whoa, that that didn't work the way that I was expecting it to. Look at them jiggling. Okay, so clearly we missed something here. Surface area times all of the rest of the stuff. Oh, I think the reason why is because the drag magnitude. Wait, no. We're having a problem because we're multiplying a vector that doesn't have something properly defined. So we need to find all of the vectors that are being created, because this is the only thing that I added, right? Yeah. So that doesn't really make sense because we're just using the same units still, I think, unless we did something silly. Surface area is equal to the mass. I'm not sure at all what is going on here. Drag magnitude, set magnitude, drag magnitude. Is it because our magnitude is too high? Return drag force. And then the drag force is used. I'm pretty sure it's used over here. Where's the drag force? Calculate drag. Drag force, apply force. Oh, it's because this isn't a vector, that's why. Calculate drag. So then the calculate drag function should return a vector. So where is drag force being initially defined? Drag force is initially defined here as a copy of the velocity. So that is indeed a vector. I'm not sure what's going on here. Not a finite number. I suspect that's not what the problem is. We can just pop in a console.log drag force, and let's just see what that value is. Okay, so at this point, drag force, these are all of the hidden functions. Side, from radians to radians. Don't have to worry about that. Okay, so it looks like our y value got to be to a ridiculous number. But I mean, it's like just like a floating point error, isn't it? Why is it that our y value is so weird? Well, of course it's the y value because that's the thing that's going down, but like why did it get so weird when we basically made this just a little bit bigger? So like if we added like just a ×4 to that, we made this like a ×10, does that do anything weird? I mean, that does do weird things. It doesn't break it in a meaningful way. Okay, I'm genuinely lost on this one. So we're gonna pretend that we did consider the surface area, and we're not going to look at that more. If I figure this out, next stream I will talk about what's going on over here. Let's see if we can move on to the next exercise, though. Boo, 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 boo. Okay, and so I'm gonna leave a note to myself to just say surface area breaks everything. I'm not sure why. And then maybe I'll just add in where we factored in the magnitude earlier. Okay, hopefully that's enough breadcrumbs to continue off of next time. All right, I'm not really sure if we're going to have enough time to finish this next exercise because I think this next exercise is a pretty big one. In addition to drag being a force in opposition to the velocity vector, drag force can be perpendicular, known as a lift-induced drag. Try creating a simulation of lift. So I guess what we would need to do here is we would probably need to make a completely fresh take on this entire example and make it so that I guess like the boxes are moving in the other direction, moving from left to right instead of up and down. Drag force can be perpendicular. I don't suppose that has anything to do with. Let me put this on a whiteboard. Force in opposition to the velocity vector. Drag force can be perpendicular, and by perpendicular, probably means like this. So then how does that contribute? Well, I guess we wouldn't need to explicitly do that. What we would need to do is we would just need to add another function that's similar to calculate drag, but instead of setting it so that it is -1, we just rotate the thing 90 degrees instead of a full 180 degrees as far as the direction for the drag force. And so that would make it so that all the boxes kind of move in a left or right direction a little bit. So I think we can replicate lift meaningfully by just adjusting our liquid thing and make it move to the left or right by just changing just this number right here. I feel like I need to revisit vector multiplication to figure out how to make things move just 90 degrees. So we're gonna do a little math search. how to multiply. Actually, let's look at the physics side of the world. Let's look at physics lift force formula. Drag lift force formula. Lift to drag ratio. I trust NASA with this, so let's take a look here. So we've got lift, we've got drag, we've got weight. Okay, so yeah, I should have put lift to be up here instead. I honestly had no idea that NASA had a guide to aeronautics textbook. This is really cool. Okay. Lift to drag ratio. So the ratio is not the thing that we're looking at. What we're looking for is how to get the right vector. Okay. So let's look at the drag equation. This is the 1/2 stuff. It's actually identical. Yeah, lift looks identical to drag. Okay, so I think we're on the right page about, I guess, just taking the same existing drag equation and then just modifying the vector. The descending right glider. The flight path is moving in a direction. The tangent, flight path, which falls to the left, intersects the horizontal thin red line at an angle called the glide angle. The glide angle, which is A, the tangent of the glide angle is also related to the ratio of the drag D, the aircraft to the lift. So then do we just apply tan to, well, I mean, the thing is that like our boxes aren't exactly flying anywhere, so I don't know that we would have a meaningful glide angle here. All right, I have a feeling we should just look at the math side of things instead of the physics side of things then. Let's look at vector multiplication, rotate 90 degrees. Just rotates the components and then negates the first component. Swap the components. Oh, I feel kind of silly for not remembering that I can just do that. Okay. So we're going to take a copy. I think instead of doing a true copy, let's actually make a new vector. For drag force, we're going to do new vector. Or actually, I don't know if we need to do new. I think it's just vector. Or how do we create vectors here? Create vector. There we go. Create vector. Did I spell that right? Yep. Okay. Create vector, and then we're going to take mover dot velocity dot y. We're going to negate this first one. I don't remember if we need to. I think we need to do -1 times that. I don't remember. I guess we can find out by just, trying it without that. Negative y vector. I'm going to do mover dot velocity dot x. Okay, and then so usually the x is defined first, but we're not doing that here. And then instead of multiplying it by -1, we are going to I don't think we need to have the negative at all, actually. I think we've already adjusted it meaningfully. And then, because the next thing was we were going to just set the magnitude, which should be similar to the drag magnitude. Let's go ahead and run that, and then they should... I'm never prepared for when the boxes move that fast. But yeah, I mean, that is a lift force. I think that's going to be all that we have time for today. I think if I timed it better, we could have both the drag and the lift force within our fluid. But yeah. Okay, so let's go ahead and wrap this stream up. Next time when we continue on this, which is going to be tomorrow, and I'm going to get you the time real quick after I finish this commercial message. We're going to work on gravitational attraction next. I'm going to share all of the links that we were looking at today in the Discord announcements. And before I let you all go, I do want to throw a quick shout out to the next stream, which is not going to be for quite some time. For me, over in the United States, it's going to be actually tomorrow morning at a very early time, which I'm not going to be awake for. But it's going to be the interview workshop with React and JavaScript. I don't know who's running this, but I do know it's going to be happening at this time. So do give them a shout out, or just like if you are awake in, I'm not going to count how many hours away that is. But yeah, that's when the next one is. If you are just getting your day started, have a fantastic day. If you are like me and you're wrapping things up, I hope you have a fantastic night. And I look forward to seeing you all in the next one. Actually, before it, I should actually throw up when the next one is going to be. It's going to be right after the Today in Global Hack Week tomorrow. And that's when we will continue working on this project. Anyway, I hope to see as many of you all there as possible. If you're not there, that's totally fine. I'm not going to be offended. I do think we're going to be running some really cool things. Actually, sneak peek of what we're going to be doing tomorrow. This part is exciting. Well, we've got gravity, and so I think gravity has some really cool, like animation-y things that you can do. There's a little, yeah. We've got attraction with a bunch of movers, the end body problem, and then I want to show this one. Yes, the galaxy simulation. This just looks really cool. So if you want to see how we get to building that, definitely do tune in tomorrow. Okay, looks like we have got a couple questions. Appreciate the shout outs. You were also amazing for sticking around this entire time. And thank you to everybody else in the chat that's been interacting. It's always a pleasure. Do we have to attend every session? No, you do not. You do not have to attend every session within Global Hack Week. There are a bunch of opportunities to do that, to tune into any workshops. We have workshop series. They are supposed to be for you to, I guess, like visit and then, I guess, like continue, I guess, between things. But like we always run our workshop series across different days anyway. And I like to run my workshops such that you don't actually have to have been to the previous one. I'm going to be doing, and I apologize to anybody who visits all of my recurring themes streams. I like to revisit all of the, I guess, like original. I want to make sure that anybody can drop into any stream and not be lost. Anyway, yeah. You want lavender ice cream right now? I'm not an ice cream person. I don't eat ice cream that often, but when I do, like, it always hits. Right now, I'm kind of craving second dinner. I had like dinner right before starting the stream, which is really early. Maybe it's just because I didn't eat much today. But yeah. Anyway, if you learned anything from today, try out some flowery ice cream. Oh, okay. One more question. Why not attend every session? You might want to get the full picture by attending everything. Well, okay, so Global Hack Week is designed for people to be able to tune into, I guess, like whatever is meaningful for them. And so anything that you missed was also going to be streamed onto the YouTube, of course. We have the YouTube channel. Just look up MLH or Major League Hacking on YouTube and you'll find us and all of the old previous streams that we've had. I do think that you can get a lot of value by attending every stream, but by no means is that a requirement to actually get anything out of the streams. So yeah, just like today, we jumped into the middle of the Forces chapter without, I guess, like doing the entirety of Forces again. So we're going to be continuing to do that every time we move forward in the future. Anyway, I am overstaying my welcome. Thank you so much, everybody, for being here, and I hope to see you all in the next one. Have a fantastic, beautiful day, night. Get some ice cream. All right. Cheers, everybody. Bye-bye.